So first, two thank yous. Thank you for attending. And I'd like to thank my wonderful co-authors, Youssef and Gail. So that's double points for Youssef for being here and for being a co-author. So today, I appreciate my title's quite a mouthful, right? The complexity dichotomy for semilinear sets in automata with one counter. I made a couple of gambles. The first gamble was that this session would be running a bit late. So I'm going to keep the presentation a little bit shorter. The second gamble I made was that Roland would nicely define VAS, and that gamble paid off. So I don't have to give so much definitions. And actually, it went better than that. He defines semilinear sets, so he's already spoken for me in some ways. But I will explain this complex dichotomy. There are some problems that are going to be easy and some problems that are going to be hard. I'll tell you about what these problems are in a minute. But first, you should probably be kind of confused, like automata with one counter. It seems like a strange turn of phrase. We'd normally say one counter automata or one VAS. And that's because we have we're using an umbrella term for three kinds of automata with one counter. The first we'll call integer one counter automata, so they have integer semantics. They have transitions in the integers, so you have one counter, not many counters. We're much, much, much simpler here. These counters can be updated by integers, and they have integer values. So for example, if I'm at state P on the left here with counter value 5, I could transition to state Q with counter value -7. That's fine. The next, natural semantics. Here, the counter value is natural and the updates are natural. And so I could go, if I had a transition from P to Q with update +12, I could go from P5 to Q17. And the last is VAS semantics. It's kind of like the middle ground somehow, the kind of strange brother of these two, which is that the counter values are natural and the updates are integers. So I'm forced to stay above 0 at all times. And so I, for example, could not have transitioned from P with counter value 5 because I would have dropped below 0, so that's illegal. I won't talk about everything. For now, I will talk about integer semantics. But first I should probably motivate, like why am I stood in front of you, like why am I talking? There are two problems. We've already heard that reachability is classic, I agree. The second most classic perhaps is coverability. So reachability asks, from a given initial state and a given initial counter value, can I reach a target state with an exact target value? And coverability is a relaxation of reachability that says, I don't need to reach the exact target counter value, but I want to be at least as large as that value. Coverability is much easier than reachability. In fact, reachability is empty hard. As a lovely warm-up, I'm going to show you why with maybe 1.5 lines. So I'm going to reduce from subset sum. The input to subset sum is n plus 1 integers, that's x1 through xn, and t, and it asks whether there is a subset of the x's that sum to t. And so what kind of integer one counter automata could I draw for which reachability holds if and only if there is a subset that sums to t? It's this one. So from p, I can choose to either add 0 or add x1, like I can choose to select x1, and then I can go and choose to select x2, and then I can choose to select x3, etc. And so it's pretty reasonable, you probably see immediately that the question of from P with counter value 0, can I reach Q with counter value T, coincides exactly with the subset sum. So it's deadly hard. And the converse is that coverability is in P. Well, it's in AC1, some pretty low-level circuit complexity paths. Don't worry so much about that. I won't overdo it. I did say I'd keep it a bit lighter. But to see why coverability is in P, there's kind of two cases. One is that you have a short run. If you have a short run, you can modify Bellman-Ford or Dijkstra that normally looks for short paths in weighted graphs. You can flip the weights around and look for effectively long or heavy paths in directed graphs. You cover the short runs using Bellman-Ford. Alternatively, if you don't have a short run, you have a long run, you're going to see a cycle. But if you've got just one counter, then only positive cycles are useful. And if you see a positive cycle, you can keep taking it over and over and over again until you have effectively unbounded value. And then all the negative updates that you see from there are no longer scary, right? You're going to be above the target no matter what. And a negative cycle and a zero effect cycle are not useful to you because they're only going to harm your opportunity to be above the target. And so then in the second case, when you have a long run, all you need to do is take a short path to a positive cycle, then pretend to take the positive cycle as much as you like, then ignore the counter values and just look at the underlying graph and try to reach the target. And so coverability is in P, this is not crazy. But these details aside, I'm going to dichotomize them into easy and hard. That's the point of the title. And the motivating question is, excluding the reasons that I just used to argue that reachability is NP hard and the coverability is polynomial unsolvable, is there something bigger? Is there something more that can inform us, like why reachability is hard and why coverability is easy? And to do this, we introduce a generalized version of reachability. This is going to be quite heavy, so just bear with me. There are examples following in less than a minute, and the examples should do a lot of justice. So I'm going to call the problem reach, brackets S. So I fix S in advance. It's a parameterized semilinear set. Don't worry if that doesn't connect with you. If it does, good. The input is kind of what you would expect. It's an initial one-count automaton, an initial configuration, and then some valuation of the parameters. So I give you the values for all of these integer parameters. I call the vector t. And then I ask whether there exists a reachable configuration qy for which the tuple of the vectors t and the counter value y is in S. Might sound strange. And what does fixed mean? Well, fixed means that I have one problem defined for every semilinear set S. So you can imagine I just give you a whole massive family of problems. Examples will help. So first, I said this generalizes reachability and coverability. I can choose this set S where I have counter values y and I want y to be equal to t. And so when I input the problem, I can input the initial configuration px and I can input the value of t that I want you to reach. And so this is reachability. Similarly, I can have this semilinear set for coverability, which is y is at least t. And well, I have semilinear sets, so I can write down anything in Presburger. I can have conjunction, disjunction. I can have modulo constraints. I can have inequality. Therefore, I can have equality because I've got conjunction. I can also have disequality. And so I can write down something more general. This is not coverability or reachability. This is cover and avoid, let's say. There's two parameters, T1 and T2. And this, for example, goes, I want to be at least T1, but I'm not allowed to be T2, right? And I could maybe do something kind of funky, like I want to belong to an interval between the value of T and 2T. Or I can do something like I'm negative or I'm in this interval. And so which problems are hard and which ones are easy? We've already seen these two. I've already told you that reachability is hard and coverability is easy, right? Unless you weren't concentrating. And then cover and avoid turns out to be easy, and reaching interval turns out to be hard. But then if you're allowed to be negative or reach an interval, it turns out to be easy. These last two are kind of surprising, like what gives? And so now I will throw on you one of our main contributions, which is the dichotomy theorem. And so let S be a semilinear set. The reachability problem to S is easy, so in AC1, if S is dense, for this mysterious dense definition, or it's empty hull if it's somehow not dense. What is density? Big formula. I will draw an example to make this clear. So let's forget the theorem just for a moment, just look at the definition of density. I will draw an example, the coverability set, right? So y is at least t. And so I'm allowed to pick any point y, and then I have to draw an interval of width, well, n either side, so the width of the interval is 2n plus 1. And I'm interested in how many points in your semilinear set A hit that interval. So I could pick the point y here, look at the interval. I will, on the right-hand side, always keep hitting the target set, right? Because the values are getting bigger. And on the left, I might start missing the target set because my interval might grow outside of the coverability set. And so here the density is at least a half, right? So on the right-hand side, I'm always going to be hitting points. On the left-hand side, I might not. Reachability, on the other hand, I've only got t. And so I have to pick y equals t. And then if I look at the interval either side, then I hit nothing, unfortunately. Like the left and the right are both empty. And so then the density of this is 1 over 2n plus 1. And if you take the infimum over all n, this diminishes down to 0. So the density of this set is 0. And now we can start looking at some of the stranger examples, like the interval between t and 2t. What happens here? Well, if I pick a y in the middle and I grow an interval out either side, eventually I'll leave the interval, right? T is given to you, and n can be as large as you like. And so the ratio here, the density you'll get, is something like, well, the whole interval is t plus 1 over 2n plus 1, and n can be much, much larger. So eventually n completely dominates t, and so the density here is also 0. But then for negative or the interval, that's not the case. Because if I place a point in this interval and I grow, I'll eventually get all of the intervals. So I get these t plus 1 points in this separated interval. And eventually I'll kind of grow my left arm until it reaches the negative points. And the worst case is when you put your point y on the very far right of this interval. So you'll get the interval, an empty space of width t and an empty space of width 2t. And so your density will be at least a quarter in this case. And instead, if you were to select y and place it on the left in the negative values, then your density will be at least a half. And so we obviously have the infimum over all choices of y, and so the density here is just a quarter. And now if I go back to the theorem, and I tell you that dense basically means density greater than 0, then you can just immediately stare at the density and go, like, those problems are easy, those problems are hard. And that's pretty satisfying. I'm kind of lying here, right? Like, where did the parameters go? And so for those who are really switched on right now, this is the full definition, but it's not really the full definition because I've simplified this a little bit for sake of presentation. I'm ignoring modulo constraints because you might say have just the even numbers, and that's actually an easy problem to decide and seemingly, yeah, it's kind of, I'm just ignoring modulo constraints. If you want to work out how to handle modulo constraints, come speak to me. And yeah, so we look at all valuations of the parameter vectors as well. Anyway, that was the first half of the talk. The second half of the talk is about an algorithm I think is really cool that I wanted to show off. And this is in the vast semantics. And first I'll talk about my dichotomy here, like which sets it easy to reach. And so we know that coverability is easy. This wasn't in the presentation so far. But the problem's the same, and you're given a one VAS instead of an integer one counter automata. And we have a similar looking but kind of suspiciously different theorem. There's a dichotomy, but the property that you have that splits you between being hard and easy is, well, now uniformly equals the upwards closed, an intimidating phrase. Let's have a quick look at what this means, roughly speaking. So you might all know upwards closed, right? You have everything above you, so 10, 11, 12, 13, etc. is an example. And delta upwards closed is similar, but you're allowed to hop by delta. So this set is 5 upwards closed, because at any point inside, if you add 5, you stay in the set. So I've got, in the congruency class modulo 0, I have 10 onwards, and in congruency class modulo 2, I have 17 onwards. And then I'll go further and define delta m upwards closed, which is delta upwards closed, but you allow m many exceptions. If I was to stick in 15 and 25, then this would be 5 upwards closed. And then in general, uniformly quasi upwards closed is over all valuations of the parameter vector that you are delta m upwards closed, but uniformly referring to the fact that you selected delta and m in advance. And that's how we split between easy and hard. But maybe let's take a step back. This is quite complicated. I'll look at the easiest example. I said if S is uniformly equal to upwards closed, then the reachability problem is in AC1. That includes upwards closed sets, so coverability is in AC1, but the state of the art before was that coverability was in NC2. If you know your circuit complexity classes, you know that AC1 is a subclass of NC2. They're not known to be equal, they're pretty close together. And so we have to improve on this already just to get a basic result about coverability, let alone in general for semilinear target sets. And so this is another nice contribution, which is that coverability is in AC1, and I'll explain a combinatorial interpretation of this algorithm. The interpretation I'm going to give you will give you a polynomial time algorithm. It will not give you an AC1 algorithm. You'll have to do a bit more work. I don't think it's worth presenting right now, but I'm happy to talk about it. But the combinatorial interpretation is rather delicious, and here it goes. So an efficient algorithm for coverability. You start with the original VAS. We'll call it V0. And then we're going to consider adding these shortcut transitions. So what do I mean by this? I look at all pairs of transitions that are connected by a state, so all interconnected transitions. So for example, here I've got P to Q with update U, Q to R with update V, and I'm looking at adding a shortcut that is P to R with update, well, U plus V. There are some scenarios in which I will add the shortcuts, and there's some scenarios where I won't. The first scenario where I will add it is, let's say U and V are both positive. Then there's kind of no difference as to adding U than adding V, though there is just a shortcut and adding U plus V. Fine. There's the situation where you end up with, let's say, U positive and V significantly negative, then there's no difference between adding U plus V at the same time. But then if you have this scenario where U is first negative and then V is first positive, what you're really doing is first checking, am I at least U, because I'm not allowed to go below 0, and then you're adding V. So somehow these two transitions are doing a bit more. They're kind of testing for some inequality and then give you an overall effect. So I'm not going to add the shortcut transition, that's too much power. In scenario 4, if you're both negative, then you're not really testing am I at least U, you're just testing am I at least U plus V, so I may as well just add this shortcut. And so I look at all pairs of transitions, quadratically many, and I add them if they fall into these scenarios, and then I define V1 by adding these, and then I define V2 by adding the next shortcuts from V1, and I define V3 by adding the shortcuts on V2, and I repeat this roughly log many times. And then the magical claim. The magical claim is that there was a run for coverability in the original VAS, if and only if there is a 2-transition run for coverability in the final VAS. We'll call it VK after you've done this shortcutting roughly log many times. I think it's just like super satisfying, disgustingly simple algorithm, and it's the kind of combinatorial reason for why we're able to get AC1. There's a lot going on behind the scenes with matrix multiplication being in AC0, but We're doing repeated squaring, which is why log is occurring. There's some AC-like things happening. Again, I'm happy to talk about the details more, but I wanted to share this interpretation. Yeah, that's roughly it. So I'll wrap up now by just throwing the dichotomies at you. You've seen already that if we're considering the integer one counter case, then density is what splits you between being easy and hard. If you've got the natural case, it's basically the same thing, but with a slightly different definition of density that I didn't present. And then this uniformly quasi-upwards closeness splits you between easy and hard when you've got fast semantics. I'll add one final comment, which is rather surprising and quite satisfying, which is if you're given an S and you're asked, is it dense, that is decidable. Same for dense plus and same for uniformly quasi-upwards closeness. So all of these density measures and upwards closed measures are themselves decidable, but those complexities are rather large. Thank you very much for your attention.